All right, here's what I think is true. We have homework due on Friday and our first quiz next class on Wednesday, right? So, okay, quiz. Wednesday, 1:25. And the first homework is due Friday, 1:27. And the homework will include the stuff that I assign today, but not the stuff Wednesday. The stuff I assign Wednesday, I'll go to the next homework, okay? And we're in the middle of talking about strains. Does anybody have any homework questions? Yep. Yeah. Mm-hmm. I know you had mentioned that in the notes and stuff like that, but yeah. I can see those applications on the work, but are those things that we're going to come across as we go along? Oh, yeah. But I'll talk a lot more about that before you need to do it in problems. Oh, okay. But yeah, it's going to be those are both going to be big topics later. No, right. Okay. Can someone pass it up? I'm surprised you, Brian. Oh, we just talked about that one. That problem is like okay. Let's talk about number 14, and then I'll talk about the changes from 14 to 13 don't have anything to do with deform, they just have to do with geometry. Okay. So this is stress tensors. Number 14. So you have a plate like this. One of the lengths is 1 meter. Yeah. And then the length in this dimension is 1/2 meter. And then the thickness of the plate is 0.05 meters. And there are 2 uniformly distributed loads applied, and they're given as total forces. So there's a total 10,000 Newton force applied straight into the plate. And then there's a force applied across the plate of 6,000 newtons. And both of these are uniformly distributed loads. So even though it's drawn as if it's a single, like a force applied as a point at the center for each of those, it's really spread out evenly over the whole thing. No part of the plate has more or less force applied to it than any other part. Yep. So you could think of it as like something. These 2 things are rubbing against each other. Oh, yeah, that's probably the easiest way to think about it. And we want to figure out what are the restrictions on the stress tensor. So what are restrictions on the stress tensor? Does it say on the top face? Yes. One thing that's interesting about problems with thin plates like this is that the stress is pretty much uniform all the way through the thickness. So even though we're calculating restrictions on the stress tensor on the top face, technically, that's going to match pretty well with the stress tensors all the way through it, just because it's a thin. You don't need to remember that, but that's sort of an aside. All right, so what we're going to use is this. We're going to use the relationship that says the stress tensor times the outward facing normal is equal to the traction vector on the face. So what we're going to do is figure out the traction vector based on these forces that are given. We're going to figure out the outward facing normal vector, and then we're going to come up with a set of equations that don't give us values for individual stress elements, but they do put restrictions on what combinations of stresses are allowable. Okay, so the traction is just equal to the total force vector divided by the cross-sectional area. And so if that total force vector, right, that is 1 over A, times the total force vector of, I haven't drawn a coordinate system yet, but let's do one that's like this. X, Y, Z. So that 10,000 Newton force is in the negative Y direction. And the 6,000 Newton force is in the positive X direction. So this force vector is positive 6,000, negative 10,000, 0. Area of that face is 1 times 0.5. So that's 1 over 0.5 times 6,000, negative 10,000, 0, or 12,000, negative 20,000, 0. And what are the units of traction? Pascals, yep. You can get that. I mean, if you ever forget that, you can always take any of these formulas where you know the things that go into it and calculate what those units would be. This is force divided by area, so it has to be newtons per meter squared, which is pascals. And now we need an outward-facing normal vector. So the face that we're interested in is this top face. And a vector that goes from the material out of the material through that face is in the positive y direction. So what's a unit vector in the positive y direction? 0, 1, 0. Yep. So this is just 0, 1, 0. And so the stress-traction relationship equation says 12,000, negative 20,000, 0 is equal to the stress tensor. And we don't know, we're trying to figure out some things about that, but for now we don't know anything. So I'm just going to label all these elements: XX, XY, XZ, XY, YY, YZ, XZ, YZ, ZZ. And then I'm going to multiply that by the outward-facing normal vector. when you do this matrix multiplication, you take a row of the matrix and the dot product of that row with the column vector. So this dot product will give you the top force component, or the top traction component that comes out of this multiplication. And then this row times this column gives you the second component of the traction vector, and so on. So you end up with three equations. The first equation says 12,000 is equal to 0 times sigma xx plus 1 times sigma xy plus 0 times sigma xz. The second equation says negative 20,000 is equal to 0 times sigma xy plus 1 times sigma yy plus 0 times sigma yz. And the third equation says 0 is equal to 0 xz plus 1 yz plus 0 zz. So what these equations tell us, the first one says xy is equal to positive 12,000. The second one says sigma yy is equal to negative 20,000. And the third one says sigma yz is 0. And these are in pascals. And that lets us, that puts restrictions on what's allowed for this stress tensor. So you can rewrite this stress tensor as, do we know anything about sigma xx? Nope, all we know is these three things. So I'll just call that sigma xx. But we do know that xy is 12,000. We don't know anything about xz. And then symmetry says this is also 12,000. Yy is negative 20,000. And yz is 0. And then symmetry says we don't know this. We know this one's 0, and we don't know this. So we haven't figured out the stress tensor, but we have put restrictions on what's possible. If you wrote out a stress tensor, we could say, yes, that's possible based on what we know, or it's impossible. And by the way, those are tiny values of stress for the kind of calculations that we'd be interested in. The only reason you really ever calculate stress is to see how much engineering materials are going to deform or whether they're going to break. And stresses in this ballpark don't cause any noticeable deformation or get you anywhere near where you'd expect any kind of engineering material to break. Any other questions on 14?
So your equations, restrictions?
Yeah.
Like when I did that, I put the one times sigma zy instead of yz.
Okay.
Does that matter?
Well, symmetry says that they're the same thing. So people do tend to write it with the lower, the lower letter first, but it doesn't change anything mathematically. Mathematically, it means the same thing.
Okay.
Any other questions? Yeah, so you always choose that that outward facing normal vector is always a vector perpendicular to whatever face you're considering. So that means that says it's either up or down on the y-axis, and it goes from material to out of the material. You know, it's like, think of it like alien.
Yeah.
You know, these unit normal vectors are like alien. You know, like that's like a unit normal vector to a guy's stomach. Yeah. Okay. I'm going to think of it that way from now on. Mm-hmm.
Can you also look at that as 0 times the vector sigma xx, sigma xy, sigma xz, 1 times the vector sigma xy, sigma yy, sigma yz, etc.?
Well, it's dot products, so you might be able to think of it. It's not. It doesn't totally immediately occur to me how you would think of it that way, but there's probably multiple ways to think about it. But you do have to remember it's dot products. So each one of these equations, you're not just multiplying like 0 times 0 times one element. You have to remember to add those elements up too. Okay, so now let's think about what gets more complicated when you go to number 13. So number 13 is the same problem. It's essentially the same. But with complicated geometry. So it's one of those things where you think like, God, this is a hard deform problem, but the deform part is still easy. If you keep reminding yourself what your roadmap is, the geometry is pain. But the idea is you have a circular cylinder and it's cut at a funny angle. So that what you really have is the shape in black. So it's like, you know, we chopped off this little corner here. And we're trying to figure out the stress on this face at this angle. What we know is that the radius of this thing is 0.02 meters. So the whole diameter is 0.04 meters. And we know that this face, if I draw it side, makes an angle of 20 degrees here. This is 70. That's the outward facing alien vector. All right, so we're given that that face has a total force acting on it that's equal to 12,000 newtons in this direction. And so the first thing we have to do, just like in number 14, is figure out the traction that's produced by a 12,000 Newton force being applied over this inclined face. That means we just have to figure out what the area of this inclined face is. So the traction vector is equal to if the coordinate system is like this, that traction vector is negative 12,000 newtons, 0, 0, divided by the area of the face. Okay, so how do we figure out the area of that face? Well, the area of the circle, so let's think about that. Before we do the incline, the area of the circular cross-section is just pi r squared. So pi times 0.02 squared. And here's the other thing that we know. The ratio of the area that we want of this inclined face so that's the area we want. It's an ellipse, yeah. Is it an ellipse? It's some kind of stretched out circle. Probably an ellipse, I'm not totally sure though.
So the triangle depends on what shape.
Yes, that's right. So I drew this angle sort of from the side, so three-dimensionally you can kind of picture what's going on. And this is just drawn straight on so you can see what all the angles are. So that's like taking this and just turning it a little bit that direction. So the z-axis is coming straight out at us. Okay, so here's the relationship you need. The area, let me call this area circle. And I'll call this A, just the area that we want. Okay, so the area that we want divided by the area of the circle is equal to this diameter that is equal to this length, like the incline diameter of this, like the height of that ellipse or whatever it is, divided by the diameter of the circle. So the area we want divided by the area of the circle is equal to L over 0.04. It's no. It's going to be just like L is a little bit longer than 0.04. This area is going to be a little bit bigger. So that no, think of it as like what's happening is all you're doing is you're taking this circle and you're stretching it up without changing any of the width dimensions. So
how is area is proportional to the diameter? Because areas, is it like diameter joint?
It's just saying that since all you're doing is stretching that circle up, all you're doing to the area is increasing it the amount that you stretch it up. Okay, because that's all you're doing to it. You're not changing the width at all. So that L is equal to Let's see. So L is equal to well, L over 0.4. I'm doing that backwards. 0.4 over L is equal to cosine of 20, right? Point 0.4 over L is equal to cosine of 20. 0.04, thanks. And so L is equal to 0.04 divided by cosine of 20. And so going back up to this one at the top and plugging this result into it, A over A circle is 0.04 over cosine 20 divided by 0.04, or in other words, this is just equal to 1 over cosine of 20. So the total area is just equal to the area of the circle divided by the cosine of 20. So the area of that inclined shape is pi times 0.02 squared divided by cosine of 20. Someone calculate that. Point 0.001337, and that's meters squared. And so now we can do the traction. So the traction is equal to 1 over that, 0.001337, times negative 12,000, 0. So what's 12,000 divided by this? Okay, and then 0. That's units of pascals. And so the last thing we need before we can use that relationship between the stress tensor and the traction is we need to know that outward facing normal. Okay, so if that's the incline, and we know that this angle is 70 degrees, you can think of it like this. X-axis, y-axis, a vector that points up along that inclined face is that. So this angle is 70 degrees. And the alien vector we want is 90 degrees from that. So backtrack 90 from there. Yep, and so theta for this is plus 20. So that outward facing normal is cosine of 20, sine of 20. Which is 0.940, 0.342. And now we can just set up the equation just like we did in 14. Traction vector, which was negative 8.9736. Negative 8.973 times 10 to the 6, 0, 0, is equal to the stress tensor, times that outward facing normal we just figured out, 0.940, 0.342, 0. And this gives three equations. The first one says negative 8.973 times 10 to the 6 is equal to 0.940 sigma xx plus 0.342 sigma xy. Second equation says 0 is equal to 0.940 sigma xy plus 0.342 sigma yy. And the third equation says 0 is equal to 0.940 sigma xz plus 0.342 sigma yz. And so this time, it doesn't allow us to figure out any individual elements of the stress tensor. But we do know that we have these three relationships that have to hold between elements in the stress tensor. And that's restrictions on the possible values that you can have in the stress.
So we just have too many unknowns.
Yeah, and that's always the case because, I mean, if you just think of it as you're using a traction vector to try to specify the traction vector has three elements. You can't take three elements and turn them into six elements, knowing six elements. So you're always going to have more variables than equations from that.
Outward, it's like, can it be seen like one?
Yeah, but that would be hard to figure out, so I'm never going to ask you to do that. But yes, it could be. I mean, if you were doing it on a face that was that was rotated like that, and then also rotated like that, then you'd have to have non-zero elements for all of them. But we won't do that. Yes. Even this form would be fine with me, really. Just the matrix form, if you want, left it like that. Oh yeah, it would get pretty ugly to try to substitute that back in. Yeah. Any other questions about that? Either of those two? Yes. Yeah, well, So basically, the idea is you start out with a circle like this. And imagine breaking this circle up into infinitesimal strips. So let's call that dy. The effect of slicing that thing at the angle, you know, that's the same effect as like projecting a shadow onto a hill or something. It doesn't change anything about the width at any point, but it changes the height. So when you do this projection, you end up with a thing that's projection of that strip is equal to dy over cosine of 20. The width is still the same, you know, so whatever this is, that's still what this is. It's just the height that's changing. But I would never make you do geometry like this on a test. I was asked about whether I might have you do this question on a quiz. Like, yeah, you should remember how to do this, I guess. But I'd never ask you to like think through like this isn't a geometry class. That's right. It's only the height changes, and that's why the ratio of the heights, or the ratio of the of those lengths of those two sides, is proportional to the areas, because only the heights in the areas change. Any other homework questions? Well, maybe I can get through a little bit of. So last time we talked about normal strains. So now we have to talk about shear strains. That's interesting that you asked. There actually is that when you put it in the tensor notation, you tend to write it all the same as that sigma. But where am I going to write this? Often you see sigma representing normal stresses, and tau representing shear stresses. I'll mention that, that's going to come up pretty soon, but yes, there is a different notation for those two. So normal strains have to do with elongation and contraction, a change in length. Shear strains have to do with changes in angles between faces. So, like for example, if this is the element you're looking at, and all of these are right angles before the deformation, after the deformation, you could have something like that. Yeah, so the faces are always going to be parallelograms. And then if you put parallelograms together, you get a parallelepiped. Now these change. The two opposite angles have to stay the same because it's a parallelogram. And so we're going to call this angle theta AB. Where theta AB is the angle between the plus A and plus B faces. In this case, well, since I'm using this coordinate system, the angle that I drew there is the angle. So for this coordinate system, that's the positive x face. That's the positive y face. And so this angle that I drew here is the angle between the positive x and the positive y. So that's the angle theta xy. Okay. What are these? This and this. What's the trick question? Because if you look at, that's an angle between the positive y face and the negative x face. And so that doesn't have a name. We're only going to be dealing with the angles between positive faces. So this is theta xy in this example. Then these are the shear strains. This is the Greek letter gamma. And gamma xy is equal to pi over 2 minus theta xy. Gamma xz is pi over 2 minus theta xz. And gamma yz is pi over 2 minus theta yz. And all these angles have to be given in radians. So remember when we talked about normal strains, there was a physical significance to whether the strain was positive or negative. If you have a positive normal strain, it means elongation. If you have a negative normal strain, it means contraction. There's a physical meaning for this too. So notice if the shear strain is positive, it means that the angle between those positive faces has gotten more acute. And if it's negative, it means that angle has gotten more obtuse. Here's an example. So let's say we start with a cube. All of these are right angles. And I'm going to use a funny coordinate system with the x-axis. The x-axis up. And the z-axis to the left. And after deformation, the shape's like this. This is exaggerated. And we're given that this angle is 1.43 radians. And the faces in the planes that aren't shown remain perpendicular. What are the shear strains? Well, first of all, we know that there's no angle change between the X and Y faces, and there's no angle change between Y and Z faces because those aren't shown. So sigma XY is, gamma XY is equal to gamma YZ, and those are equal to 0. So the only one we have to figure out is the one in the XZ plane. All right, so the next thing we have to do is figure out which of these are the positive faces. So what's the positive X face? Usually the positive X is over here, but in this case, yeah, that X-axis is like an alien also. So that's the positive X face. And positive Z face? Right. Left. Depends which way whether you face your paper or not. Okay, so this is the plus X. This is the plus Z. And so the angle we want is this one. So how do we figure out what that angle is? This is theta Z. Yep, that works perfectly well. You can also, these angles have to add up to pi in a parallelogram. So theta xz plus 1.43 is equal to pi. So theta xz is 1.71 radians. And so gamma xz is equal to pi over 2 minus 1.71, which is negative 0.1392. That's horrible significant figures. It's radians, right? So it's unitless. Just so all strains are unitless. Does it make sense that we got a negative answer? It does, because the angle that we're looking at got more obtuse. Okay, so even though this one got more acute, this is the one between the positive faces, and it got more obtuse. So it should come out negative. Yeah, something went wrong if you know it got more obtuse and it's positive. Yeah, it's the change in angle between two faces. And it's what happens if you look at this. I gotta visualize. So it's what happens if you have forces that do this. See it better this way. Okay. It's so when two things do what shears do, one pushes this way and one pushes the other way, it has the effect of turning a square into a parallelogram. Yeah, that's right. Yep. Yes, that's exactly right. Yep. Okay, one thing to notice again, that value is like all of these examples have been, that value is way too high for our purposes. No material, it's still in its linear range, behaving elastically with a strain that big. So realistic shear strains for us will be less than about 1.0 times 10 to the minus 4. If you get anything bigger than that, our approach is not suitable for the calculations. Any questions? All right, that's all.